In the Hollywood thriller Angels and Demons, terrorists steal a fraction of a gram of antimatter to blow up the Vatican. The fiction actually gets the physics right. When antimatter meets normal matter, they instantly annihilate. Einstein's E equals mc squared takes over, converting nearly 100% of their combined mass into pure energy. The real story starts in 1928, when physicist Paul Dirac found a strange negative solution in his quantum mechanics equations. It pointed to an entirely unknown mirror image particle, identical in mass to an electron, but carrying the opposite charge. This shows the logic of the Big Bang radiation catastrophe. In the early universe's intense heat, matter and antimatter should be created equally. As it cooled, every particle should find its mirror twin and perfectly cancel out. If that math balances exactly, the cosmos should be a vast void filled with nothing but leftover radiation waves. You, the Earth, and the stars should not be here. Look at this visualization of the early universe. It shows that for every 1 billion matter and antimatter pairs that perfectly destroyed each other, exactly one normal matter particle was left standing. Every single galaxy, ocean, and living cell in existence is built completely from those incredibly lucky leftover anomalies. To get that specific survival rate, the laws of physics governing matter and antimatter cannot be perfectly symmetrical. There has to be a microscopic, undiscovered difference in how they behave. Finding that discrepancy means we have to test antimatter directly. We have to somehow manufacture, catch, and study a substance that destroys itself the moment it touches anything. Deep underground in Switzerland, the CERN antimatter factory is the singular facility on Earth built to actively mass-produce this volatile substance. This animation shows how they make anti-protons. They accelerate normal protons to 99.93% the speed of light and smash them into a dense iridium target. The impact is so violent it breaks the strong nuclear force holding the particles together, spawning a chaotic shower of new quark and antiquark pairs. In a parallel process, they fire electrons into tungsten. The electrons rapidly break, releasing high-energy gamma rays that occasionally convert their momentum directly into electron-positron pairs. But the output of both these collisions is a mess. The resulting particles are traveling at massive fractions of the speed of light in every direction. Producing the rarest substance in the cosmos is useless if it's moving at 100 million kilometers an hour. If scientists can't tame its speed before it touches the physical world, it will just slam into the walls of the machine and detonate. To solve the speed problem, CERN uses the ELENA decelerator ring. Strong electromagnetic fields grab the chaotic antiprotons and force them to slow down to a 1.5% the speed of light. Once slowed, the antiprotons are delicately merged with the positrons. If the timing aligns perfectly, an antiproton captures a positron, assembling a complete neutral antiatom, antihydrogen. But neutrality is a fatal flaw. Without an electrical charge, standard magnets can no longer grip the atom. Left alone, the antihydrogen will drift freely until it hits the metallic wall of the chamber and annihilates. This diagram outlines the solution, a penning trap. By combining complex magnetic fields with an electric force field and a near absolute zero vacuum, researchers can grip the particles from all sides, keeping them perfectly suspended motionless in a void. Humanity successfully engineered a perfectly empty cage. By ensuring the antimatter touches absolutely nothing, an uncontrolled explosion becomes a stable test subject. Now that we can hold antimatter, we can run experiments like G-bar. The goal is simple. Drop an atom of antihydrogen and see if gravity pulls it down like normal matter, or if it falls up. Looking for these weird discrepancies is entirely logical. In 1956, physicist Chien-Shiung Wu ran an experiment proving the universe actually favors left-handed particle spins over right-handed ones, establishing that supposedly unbreakable physical laws can in fact fail. To get the precision needed for this specific drop test, scientists have to create an antihydrogen ion and laser cool it to a fraction of a degree above absolute zero. It requires intense, multi-year engineering just to watch a single atom fall 20 centimeters. If that atom accelerates at a slightly different rate than normal hydrogen, it shatters a foundational concept called CPT symmetry, breaking the standard model of particle physics entirely. Measuring a microscopic discrepancy in a 20-centimeter drop holds the power to finally explain why that 1 in a billion particle survived, answering why the universe didn't destroy itself at the beginning of time. The technology to study these particles is scaling up quickly. CERN's BASE experiment recently managed to keep antimatter safely trapped and isolated for over 600 days. Because they built a portable penning trap with independent cooling and power systems, researchers can now keep the antimatter suspended in a magnetic box, get it loaded onto a truck, and physically ship it to other labs. But while CERN spends billions trying to manufacture and move this elusive substance underground, it's actually far closer to home. The trace amounts of radioactive potassium found in an ordinary banana naturally emit a positron every 75 minutes. In fact, the natural radioactive decay inside your own body produces around 180 positrons every single hour. While science builds massive machines to find the origins of our existence, you've been a microscopic antimatter factory all along.